In this video, we're going to be looking at rational exponents. Now, let's start by understanding what a rational exponent is. Well, from the sounds of it, we know it's going to be an exponent, so it's going to be a number that's going to be up in the air. But a rational exponent specifically is an exponent that is a fraction, and that's what I'm showing here on the top of our page. Now, that exponent that's a fraction obviously is going to have a numerator and a denominator. In the previous video, we talked about the denominator represents the root. Well, now we need to understand that if there's a number in the numerator other than 1, that number represents the power. So we have the power over the root as our rational exponent. Now, there's a couple of ways that we could simplify a rational exponent. That's illustrated in this box here. Now, let's look at the second one. The second one, what that's telling you is that you would apply the power first and then the root, which does not always make sense to do something like that. For example, let's say if we need to simplify a problem like this one, like I have 81 to the 3/4 power. If I broke that up into the power and then the root, so if I applied the power first and then took the root, what that means is that I have to take 81 cubed. I have to take 81 times 81 times 81. And to do that without a calculator or just a very simple, just a baby calculator, that would be a real pain to try to take and multiply those together, because you get a really large number, which I guess using a calculator, a baby calculator, or a simple calculator would not be that big of a deal. But then to try to figure out what the fourth root of that really large number would be rather difficult. And to try to do that by hand, I just wouldn't even want to start. So a simpler way to do that is that way that I have highlighted here, and that would be where we apply the root first and then the power. Because applying the root is actually going to make that number smaller, and then when we apply the power, the exponent there, it's going to make that number larger. So let's look at this 81 to the 3/4 power. What that means, again, is we're going to apply the root first and then the power. So we're going to take the fourth root of 81 and then cube it. So the fourth root of 81, well, that's just 3, because 3 times 3 times 3 times 3 would give us 81. And now we have to take that 3 and we're going to cube it. 3 cubed would end up being 27. So 27 would be our answer. So we were able to do that without the use of a calculator, where if we had done it the other way around by applying the power first and the root, we would have absolutely wanted to use a calculator. Well, down below here we have some examples that I'm going to have you guys do. So why don't you guys go ahead and pause the video at this point and hit play when you're ready to check to see if you have the correct answers. And so we're going to work on these two down below here. Okay, let's see how you did here. For this first one, you should have applied the cubed root first to the 64 and then squared it. Well, the cubed root of 64 is 4, and 4 squared is 16. For the second one, apply the root first, so this would be the square root, and then apply the power last, which would be the third power. So the square root of 100 is 10, and 10 cubed is 1,000. Now we have these different properties that you've probably seen before, but it's important to get down in our notes. So why don't you guys go ahead and pause the video so you can make sure you copy all this down into your notes. You won't be expected to know the names of the properties, but it'd be still good to have those so you have something to reference them by. But write down all these properties. So pause the video and hit play when you're ready to hear me explain what each of these are talking about. Okay. So this first one, the power of a power property. That's saying that if you have something inside of parentheses, like x to the a power, and an exponent outside the parentheses, basically all you have to do is multiply those two exponents together. That's all that property is telling us. The next one is telling you that if you have where you're multiplying and the bases are the same, you don't actually multiply the numbers. What you're going to do is you're going to add the exponents. So if you had like 3 squared times 3 cubed, well, the 3 would stay the same, but what we're going to do is we're going to add the exponents. 2 plus 3 is 5, so it'll be the same as 3 to the 5th power. Well, division is the opposite of multiplication. So if you're dividing and the bases are the same, we're going to subtract the exponents. If you're multiplying items inside of parentheses and you have an exponent outside the parentheses, that exponent applies to everything inside the parentheses. So the x and the y would both be raised to the b power. Same thing is true with division. If we're dividing inside of parentheses with an exponent outside of there, that exponent applies to both the numerator and the denominator. The zero exponent theorem tells you anything to the 0 power is 1. And lastly, the negative exponent theorem tells us if we have a negative exponent, all we have to do to make that negative exponent positive is to take the reciprocal, of the base. So why don't you guys copy down these examples into your notes, because we're going to go through a couple of these together, and I'm going to have you guys work on some of them on your own. Let's look at these first two together. For this first one, 49 to the negative 3/2 power, well, there we have a negative exponent. So I'm going to take the reciprocal of the base. The reciprocal of 49 is 1 over 49. Now by taking the reciprocal of the base, it makes that exponent positive. Now that 3/2 we've learned applies to both the numerator and the denominator. So I'm going to write this as, I'm going to break that up into the root and the power. So the denominator, we're going to do the same thing. We're going to apply the root and the power there as well. Now with the numerator, that's just going to be 1. The square root of 1 is 1. 1 cubed is 1. The denominator, the square root of 49 is 7. And now we have to figure out what 7 cubed is. Now on the quiz or the test, you'll be able to use a baby calculator at this point. But your baby calculator will not have an exponent button. You just have to know that 7 cubed, we'd have to use repeated multiplication and take 7 times 7 times 7 to get 343. And we would leave our answer as a fraction, not as a decimal. Now the next one is not a negative exponent. The next one, we have 64 over 729 being raised to the 4/3 power. But again, we would apply the root and the power to both the numerator and the denominator. So I'm going to look at this as being 64 to 1/3 power being raised to the, third root of 64 being raised to the 4th power. Do the same thing to the 729 in the denominator. Apply the third root and then the 4th power. Well, the third root of 64 is 4, and 4 to the 4th power, again, I don't expect you to memorize that, but 4 to the 4th power, if you use a calculator and repeated multiplication, we end up getting 256. In our denominator, the cube root of 729. Now, using your calculator, again, even with the baby calculator, there's no way to get directly to your answer. What you have to do with a problem like this is you have to think about your number sense. Well, we can see it's an odd number, so the cube root of that is not going to be an even number, so it can eliminate all the even numbers. And we're looking to find a number multiplied times itself 3 times, that's 729. So it's going to be a number between 1 and 10, basically. And we can eliminate, like I said, we can eliminate 5 even. 5 is an odd number, but 5, if you were to apply any exponent to a 5, it's going to end up with a ones digit of 5. So it's not going to be 5. It's not going to be 6, because 6 is even. 7, if you tried 7, 7 cubed is not 729. 8 wouldn't work because, again, 8 is an even number. But 9 would work. 9 times itself 3 times is 729. And 9 to the 4th power, again, you'd have to use repeated multiplication there to get 6,561. And that would be your answer. So why don't you try these other 4? These other 4 are not going to be quite as tricky as letter B. But why don't you work on those? So why don't you pause the video and hit play when you're ready to check to see if you have the correct answers. Okay, see how you did here on letter C. So again, we have a negative exponent, so we take the reciprocal of the base. The reciprocal of 16 would be 1 over 16. So now we'd have to the 3/4 power. Again, break that up into the root and then the power for both the numerator and the denominator. And the numerator just is going to stay a 1. The 4th root of 16 is 2, and 2 cubed would be 8. For letter D, this is another negative exponent, so we take the reciprocal of the base, so it's 1 over 64 to the 2/3 power. Again, break that up into the root and then the power for both the numerator and the denominator. Well, the numerator stays 1. The cube root of 64 is 4, and 4 squared is 16. For this one, this is not a negative exponent, so it stays at 64. So now we're just going to take the square root of 64 and cube it. Well, the square root of 64 is 8. 8 cubed is 512. And lastly, we end up getting for this one, this is a negative exponent. So we take the reciprocal of the base to make that exponent positive. The reciprocal would be 625 over 81. For the numerator and the denominator, we're going to break that exponent up into the root, then the power. So we take the fourth root of 625, which is 5, and 5 cubed is 125. In the denominator, take the fourth root of 81, which is 3. 3 cubed is 27. Well, let's look at these problems. These problems are applying those rules now with a slightly different twist on them. We want to figure out what 1/2 to the n over 12 as your exponent would be as a power of 2. In other words, when it says we want to rewrite that as a power of 2, means that the base is going to be a 2. Well, the 1/2, basically all we'd have to do is change that to be 2 to the negative first power. Because I haven't changed anything here, I haven't changed the value, I've just changed how it looks. Because if I took 2 to the negative first power, the reciprocal of 2 is 1/2, so now I'd have 1/2 to the first power, which is the same thing as what we have originally. Well, I want to simplify this. I'm going to multiply these exponents. My exponent's going to be a negative n over 12. That would be my answer. Now the next one's a little bit trickier because we have 1/9. Well, and we want to write this as a power of 3. Now the previous one was easy to see because we had the denominator was already a 2, but this one is not. We might recognize that 3 squared would be 9, so what we would have here is 1/3. If I were to square that, I'd get 1/9. And then we would have the negative 2/5 still. But again, I want to change that base to be a power of 3. So we want to change this to be a negative exponent here. So again, I haven't changed the value, I've just changed how it looks. Because if I were to go backwards now, 3 to the negative second power would be the same as 1/3 being squared, and 1/3 squared is still 1/9. So again, I have not changed the value, only how it looks. But now we're going to multiply these two exponents together. Negative 2 times negative 2/5 would be a positive 4/5. And that would be my answer, 3 to the 4/5 power. Now in these next two examples, we're going to be changing how something looks. So here it's in radical form. We want to change it to rational form. And again, to review, rational form is what we talked about at the beginning of our notes. That's in the form x to the m over n as their exponent, where m represents the power, n represents the root. So for this one, my power that it's being raised to is the 5th power. My root that I'm using is the cubed root, so it'd be r to the 5/3 power. The next one is written a little bit differently. We don't have parentheses around the whole thing. It's only the 9 that's got being raised, or it's only t being raised to the 9 power. But it's still written the same way. My power would be 9, so it's going to be my numerator, and is where the 9 goes. The denominator is where our root goes, so it's going to be the 4th root. So we'd say t to the 9/4 power. Now the next one you might say, well, this one already has it's not written in radical form, it's already being written as an exponent. Well, remember rational form, the exponent needs to be written in the form of a fraction. So we need to change that negative 0.3 to be a fraction, and 0.3 would be the same as 3/10. And if you didn't get that, if I had 31, or the reason why that we were using 3/10 is because 3 is in the 10th place. If I had 31 instead of 0.3, if I had 0.31, the 31 would be in the hundredths place. So we'd have 31 over 100. But now let's look at these next examples. These next examples say to write using a radical. Now a radical is this symbol. So we want to write these the way that the original problems in the previous example were written. Now there's two ways you could write these. For this first one, this is the 8th root of our our power is the 7th power, so you could write it like this, or we could write it like this, where we have the 7 outside the parentheses. Now when we deal with negative rational exponents, my root is always positive. So we're never going to have a negative root. So our root is always going to be positive. So I could say that this is going to be x to the negative 8th power, the 5th root of x to the negative 8th power, or I could write it like this, with the exponent outside the parentheses. So either one of those answers would be correct. Now let's look at this little statement. This is kind of a unique thing. This is a loophole that we have with rational exponents. When we work with rational exponents, the base must always be positive. And the reason why is because of this loophole. Now, the cube root of negative 8, that's okay. The cube root of negative 8 would be negative 2, because negative 2 times negative 2 times negative 2 would be negative 8. However, negative 8 to the 1/3 power is not always the same as negative 2. You might say, well, why is that? Wouldn't it be the same thing? Well, let's look at this. I'm going to show you something that does not break any rules of math, but we will get a positive 2 as our answer. Here's what I'm going to do. 1/3 is the same as 2/6, right? Because 2/6, I could reduce that to 1/3. So there's nothing wrong with this so far. Well, remember those different rules at the very beginning to simplify a rational exponent. Remember I said the majority of the time we're going to apply the root first and then the power. But we have that theorem that says you can apply the power first and then the root. So for this problem, I could apply the power first and then take the 6th root. So negative 8 squared is a positive 64. And now if I apply the 6th root to 64, well, that's a positive 2, which obviously is not the same as negative 2. So because of this loophole, where I could change the 1/3 to 2/6, because of that loophole, our base has always got to be positive when we're working with rational exponents. Well, let's end this video by looking at this last example. Here we're going to use the fact that v equals s cubed, and s is referring to the side length or the edge length cubed. Some books will use e instead of s. Or the surface area can be found by taking 6 times the side length squared, or the edge length squared. We want to use that information to find the volume of a cube with a surface area of 105 square inches. So what I'm going to do is I'm going to start by using this formula, because my goal is to figure out the volume. But in order to find the volume, I need to know my length s, or my edge length. So what I'm going to do is this. I'm going to start out with the 105 and say that's equal to 6 times s squared. Well, I could solve for s now by dividing both sides by 6. Doing so gives me s squared. 105 divided by 6 is 17.5. Take and raise each side to the 1/2 power, or the square root of 17.5 gives us 4.18. So each side here would be 4.18 inches. So now to find the volume is going to be the side length, or the edge length, cubed. So my volume, 4.18 cubed, is 73.2, and this would be in inches cubed. Would be my answer. Now what if I had to do this a number of times? It would be better if I had a formula that would get me directly to my answer, and that's what they're asking for here. It says express the volume of a cube as a function of its surface area. So originally, the formula for our volume is written as a function of its side length, or its edge length. So we want to change that up so it's a function of its surface area. So how do we do that? Well, we're going to do the same process that we did in the previous problem. I'm going to start with my formula as the surface area is equal to 6 times s squared. So I'm going to get the s by itself, so I'm going to take and divide both sides by 6. So I get s squared equals my surface area divided by 6. So to figure out what s is, we take the square root, or in this case it would be easier to take and raise each side to the 1/2 power. The reason why that's easier is looking at our next part. Again, my goal is to find a formula for the volume in terms of my surface area. So remember, the volume is the side length, or edge length, cubed. Well, I just found that edge length is this. But now we're going to take that side length, that edge length, and cube it. Well, we have that form, or that theorem, that property that tells us we can multiply these two exponents together. So the formula to find the volume, written as a function of its surface area, would be this. And that would be my answer. So it would be the surface area divided by 6 raised to the 3/2 power. So now that I have that formula, if I wanted to, for this previous problem, I could have just put 105 in for my surface area, Divided by 6, raise that to the 3/2 power, and you'd also get 73.2 square inches. So that's it. That is our lesson on how to use rational exponents. So with that, good luck now as you work on your assignment.